Good day, everyone. So today I'll wrap up the preliminaries of uniting the different ways of generating the Jacobi elliptic functions, and then one more video on the differential equations that they're useful for, and specifically solving the pendulum equation with the elliptic functions. All right. First, a quick look at the two methods. I call this method 1. This is with the vertical ellipse. And from here, you take any point on the ellipse and you just go in a straight line towards the unit circle, whether it's towards the origin or away. I do both the ellipses beyond the unit circle, but just go straight towards the unit circle, and then we'll get all the properties of the Jacobi elliptic functions and their derivatives this way. So this is with the vertical ellipse, and the U matches a little better with the standard definition, as we see there. And here is our other way of generating the Jacobi elliptic functions. This way is with the horizontal ellipse, and instead of going straight to the origin towards the unit circle, we use the equation of the ellipse, which I don't have here, but it would be x over a quantity squared plus y over b quantity squared equals 1. So we just let kun u be x over a, sun u be y over b. Common option is to have b 1, in which case kun u is x over a and sun u is just y. And that's the ellipse on the right. So here is a side-by-side comparison of the two methods. One important thing to note with both, du is r divided by the minor axis d theta, which is r over a for the vertical, and it's r over b for the horizontal. But it's r divided by the minor axis d theta is du for both cases. Also, theta and phi are the same angle in the vertical ellipse, and I only drew in the phi, but that's also theta. In the horizontal ellipse, the angle theta to the point on the ellipse is different than the angle phi to the point on the unit circle. And of course, if we were to solve for the polar form r in terms of theta, we get different equations depending on if it's a vertical ellipse, major axis vertical, or whether it's a horizontal ellipse, major axis horizontal. So we have two different integrands, but there's still a way to resolve the two forms, which I will do. So what I first want to also do is look at what happens if I were to interchange the ideas of getting to the unit circle from the two methods. So for example, from the horizontal ellipse, if the minor axis is 1, for convenience I'm looking at that case, kun u is x divided by the major axis, sun u is then just y, dun u is r divided by the major axis, and then du is r d theta. So if I were to do that for the vertical ellipse, now the major axis is b. So if I'm on the ellipse, I'm going to go straight down. So x will just stay kun u in this case, and then the y will be y divided by the major axis is what I need to get to the unit circle. So sun u will be y divided by the major axis b. And similarly, dun u will be r divided by b, but du will still be r d theta. So I'm going to use that idea for the horizontal ellipse. On the vertical ellipse, we almost get what we still have for the Jacobi elliptic functions, but there's just a slight change. And then I'll also compare going the other way. So if I just go straight to the unit circle on the horizontal ellipse, the same kind of thing will happen as I'll show right now. So to try that same idea, we will get r as the integrand, perhaps that we want this way. But the problem will be, again, x squared plus y squared over b squared is 1 for this ellipse. So we'll get that identity. But here, if you go through the math, instead of getting dn squared is 1 minus k squared sn squared, it ends up being dn squared is 1 minus k squared cn squared, which will affect the derivative. We actually get the same derivatives. I won't go, well, it looks like, I have the work, but the derivative of cn, or cnn, will be negative sn dn, so that works out. And similarly for the derivative of Sn, but the derivative of dn, since it depends on the derivatives of Cn and Sn, well, in this case, it would end up being positive. The upshot is that if you try to do the Jacobi elliptic functions with a ellipse in this way, what I tried to do as Cn is actually what the true Sn is, but of the quarter period minus u. And then the Sn, as I tried to define it, will end up being what the true Cn is of the quarter period minus u. And the dn is dn of k minus u, or k is the quarter period. I wrote it this way. So, in a way, they're similar functions, but they would just be a little bit different. So they would be like this. The same thing happens if I try to do for the ellipse, which is major axis horizontal. If I just go straight to the unit circle, like I just did for this vertical ellipse at the start of this long video. So if I did Sn is y over r, Cn is x over r, dn 1 over r. I'm keeping the minor axis 1. Then essentially the same thing is going to happen. We'll get this identity, but the other identity is 1 minus k squared. And if you do the derivatives, they'll work out. Derivative of Sn will be Cn dn. And I won't get the others, but it's, the same thing will happen. That how I just defined the Cn is actually what the true Sn is, but of k minus u. In fact, so you can check the derivatives this way. So if I want du of how I define the Sn, so I distinguish it with Snn, it would be like differentiating this function. And what's the derivative of Cn of something? Well, it would be the negative of Sn dn. But then I'd also have to do the derivative of the argument, which would give me another minus 1. So it'd be the negative of Sn dn, which are these two, but then times another negative 1, those two negatives make a positive anyway. So it would work out. And you can check everything works out. Okay, and now let's finally get the relationship between theta and phi so that the integrands really kind of give the same version of u, so we can get the same Jacobi elliptic functions regardless of which way we define or generate the Jacobi elliptic functions, whether I do it with the horizontal or the vertical ellipse. Again, they have different integrands, which means they're different, but with the right theta, we'll get the same u. So I will look at that now. So if I want to look at the relationship between x, y, and x over a and y over b, I can note the tangent of this angle, theta, is going to be y over x. And if I just call this phi, the tangent of this angle will be y over b divided by x over a. But not only is tangent phi y over b divided by x over a, since I'm on the unit circle, I can also say the sine of phi is y over b, or y is b sine of phi. And the cosine of phi, it should be cn of u, but it'll be x over a. So x will equal a cosine of phi. So the relationship between theta and phi is tangent theta, tangent phi. I'll turn the b over a into square root of 1 minus k squared there. And so we get this relation. Tangent phi is 1 over square root of 1 minus k squared y over x, but that's just tangent theta. And conversely, theta is the arctan of square root of 1 minus k squared tangent phi. Right, so we have this relationship here. I can multiply by square root of 1 minus k squared. Note also, cosine phi is x over a, sine phi is y over b. So in other words, x is a cosine phi, y is b sine phi. So that puts me on the ellipse. So this will parameterize the ellipse. But with the standard definition, it'll be the same value of phi, which gives me the cn of u. Right, so everything's all related there. So if this relates, then if I look at the two definitions of u, before I go too much further, I mean, this holds and for all values of theta and phi, and I've got a graph. It's an implicit equation. We want the curve that goes through the origin. So here's the implicit curve, and I was able to work with that. So there is one that goes through the origin. I got this branch will go 0 to 2 pi, which I use below, but there's the implicit curve. I actually had to graph without the trouble. So if you divide by cosine phi, I get the tangent phi right here, and divide by cosine theta, I've got the tangent theta. So the tangent theta is the square root of 1 minus k squared tangent phi, which I didn't write but could have had. So tangent theta is square root of 1 minus k squared tangent phi. So that describes the relation. So not only does that give the relationship between a point on the ellipse and this point on the unit circle described this way, again with the horizontal major axis, but it also gives the relationship between theta and phi needed for the two definitions I have for u. So I have u in terms of theta with the horizontal ellipse with the cosine squared integrand, and u in terms of phi has the sine squared integrand. So different integrands will mean I'll get different values of u for the same values of theta and phi, but with that relationship, they'll graph to the same u. In other words, with this relationship, I did go back to where b was 1 here, but in the end it's the same. Tangent phi is 1 over the square root of 1 minus k squared tangent theta. So with this relationship, these two integrals will be the same. So if I stick with quadrant 1 values, I will replace theta. This is theta in terms of phi. It'll be the arctangent of square root of 1 minus k squared tangent of phi. Here it is right here, so I do have it. So there's theta in terms of phi. So if I put that as my upper limit, then I'm going to claim these two values are the same, even though the integrand's different, but now the upper limit's different. And you can just do it by taking the derivative, take the phi derivative, sub in. I had to do some simplifying, right? So if I plug this in, then what's the value of cosine of this quantity? Well, I'll let theta be this value, or tangent of theta then is this quantity. Tangent of phi, sine over cosine, opposite over adjacent. So if I make a triangle, since I'm working with quadrant 1 angles, C by the Pythagorean theorem will be like that. So cosine will be the adjacent over the hypotenuse. And cosine squared will be this. So now if I continue with the differentiation of the left-hand side, I can sub this in for cosine squared, like I did. And now the derivative of the argument, well, the derivative of the upper limit, right? So I plug the upper limit into the integrand, got cosine squared, which was this, derivative of this, take the derivative, arctan, 1 over 1 plus argument squared, derivative of the argument. And since secant squared is 1 over cosine squared, I'll just distribute it across the bottom. So I'll get cosine squared phi. Tangent squared times cosine squared will be sine squared. If I distribute the sine squared, I get sine squared plus cosine squared, which is 1, minus k squared sine squared. So that's what I get that there. These two cancel. And now I have top and bottom are the same, except one's the square root at the top, so it'll be that. So this is what I get for the derivative, but that's the right-hand side as well. The derivative of the right-hand side, that's easy. Just plug the phi in there. Because we mainly dealt with squares, it really didn't matter the quadrant, actually, that we were in. But I did do it more implicitly before. That was in another video, so I won't rehash it. But I'll just keep it in the documents if anybody wants. Again, if I want to remind us of what's going on, this is the integrand for the horizontal ellipse definition. So I had 1 minus k squared cosine squared in the denominator, square rooted. And this is the integrand for the phi definition. I've got square root of 1 minus k squared sine squared t in the denominator for that integrand. And for any value of phi, there's a corresponding value of theta to get the same area under the curve. We can see it here. All right, so I'm always getting the same area under the curve. For whichever value of phi, there'll be a value of theta. And the relation is given by that, the tangents and the square root of 1 minus k squared. Which also means, let me regraph. So I'll do SNU this time. I'll do a little beyond the regular period, so I'll go to 10. But then for phi, I have to go to 5 pi over 2. So the t is really my phi. So I'll graph SNU. This will be over 5 quarter periods. And each quarter period is about 2 units, and there's a tick mark of 1, as we see in the horizontal. This is with this definition, k equals 0.8. So this is what I'm graphing. There's my x with k equals 0.8. And I had to use a u here, and a t is the upper limit, and then sine of t. But now look at the other definition, the horizontal ellipse definition. So with this, I can graph SNU if x is this integral with the cosine, but then y, instead of just being sine of phi, it was the y value on that ellipse, which ends up being r sine of theta. More generally, the y value divided by b, but b is 1 here. We got our integral. We'll go from 0 to t. I really want it to be theta, but it's not an option. Of the integrand, I don't even have to use u here, but I will use u. So that's x, and now y will be r times sine, but it's sine divided by that square root. Oops, I should have. I'll just do one at a time here. So let me not graph this one. If I look at the graph, yeah, it's right there. So let me add in the other graph then. We're Wish it wasn't so thick, but kind of see it moving along. So it's the same graph, of course. So finish graphing. If I trace, go to both curves. See I'm on x1, y1, x2, y2. Of course, both at the origin. Let's go to pi/2. And then x values, the quarter period, the k, so the 1.99. And that's for the first curve and for the second curve. I'll go to 2 pi. I think there'll be some rounding errors, but we'll see. Yeah, maybe not. So y is 0. That's on the first curve. Pretty much 0 on the second curve. So, I mean, it's calculator error there. So, of course, they match at the quadrant angles. If you picture the ellipse, the parameterization as you go around, if phi is 0, pi/2, pi, etc., you're going to be on the quadrant angles, and phi and theta will match there. But for values in between, they won't. So if I go to, say, 1, and then if I go to the other curve, so this is for the first, they're at different places. But that's inputting phi equals to 1 and theta equal to 1. So here's t equals 1 on the first curve. If I go to the second curve, it did leave t equals 1, but if I go to 1 on the second curve, I mean, it's not going to match. So there's different value. The y value is very different. Let me go back to the second curve. If I go to 0.7515, 227, might be enough decimals. That's the same x and y value. All right, so I just did the arctan square root of 1 minus k squared, which is actually 0.6, but decided to leave it in that form, tangent of that value. So I plugged in this value for theta, and I'll get the same value as if I plug in this value for phi. So when phi is 1, I'll get the same u and CNU, SNU, as when theta is this value. All right, I think it's time I wrap up this video and wrap up my ways of generating the Jacobi elliptic functions. There's kind of two main ways from ellipses, vertical, horizontal, and the vertical matches a little better, I think, with the standard definition that you'll see. But regardless, they both have some interesting things about them. What I will finally do is look at the differential equations that Jacobi elliptic functions solve. I'm going to focus on the pendulum equation. I'll probably look at that solution two different ways, and maybe even look at the graph of a pendulum and so forth. So finally ready to wrap up. If anybody got something out of this, then that makes me happy. So hopefully there are some of you out there that enjoyed this and made it through. And thanks for watching, and have a good rest of your day. Thanks again.